The outline for this chapter is as follows. First, we are going to provide some definitions related to combinatorial analysis. We are going to mention about the countability and the sets which are countable, and we are going to define two concepts which are going to be used very frequently in our class, the experiment and the outcome. Then we are going to talk about the basic principle and the generalized principle of counting, following with the concept of permutations. We are going to define what a permutation is and how can we count the number of permutations for distinguishable and indistinguishable objects. Finally, we are going to end with defining the concept of combination, and we are going to learn how to calculate the number of combinations. We are going to mention about the binomial theorem, which is going to be useful in our future classes, and finalize the course, this chapter, by defining the multinomial coefficients. So let's start with defining combinatorial analysis. Now, the combinatorial analysis is the mathematical theory of counting. So actually, counting is a simple concept, as you may think. However, it depends on the set that we are going to count. And most of the probability questions in real life can easily be answered by knowing how to count. And what is counting, actually? So if we are going to learn about it, we first need to understand counting from a mathematical perspective. First of all, when we count something, what do we count? So we always count the number of elements in a set. There should be a set, and the number of elements in that set is going to be counted if you are going to count something. Now, there are some sets which are uncountable as well. Not every set is countable. So here, set A is a countable set. How do we understand if a set is countable or not? A set is countable if its elements can be put in a one-to-one correspondence with the sequence of positive integers. So this Z plus represents the set of positive integers starting from 1, 2, 3, and it goes to infinity. We are using the elements of this set to tag each element in set A. So we say that this red diamond is labeled with 1, this green triangle is labeled with 2, this yellow square is labeled with 3, so on and so forth. We are tagging, or we are labeling each of the elements in set A with a positive integer. And when we are done, when we complete tagging all of the elements, the counting process ends. So as you can see, we have tagged all of these elements with the positive integers until number 5. So this set has 5 elements, and this set is countable. Let us give a few more examples to countable sets. For example, the earthquakes happening in 2018 are countable. Okay, so we have observed many earthquakes in many geographic lands on Earth, and all of these earthquakes, they create a set, and this set is a countable set. We can simply count the number of earthquakes that happened in 2018. Or if you imagine an urn which contains too many marbles, these marbles, they create a set which is also countable. The human population is also a set, is also countable. So there are some sets which may have infinite elements, however, still countable. Now, if you check the positive integer set, this set has infinitely many elements. However, the set itself is countable, okay? Because we are defining the countability on positive integers. The positive integers itself must be countable as well. The fact that a set has infinitely many elements does not indicate that it's not countable, okay? So there are sets such as set A here, which has finite elements and countable, and there are some sets which have infinitely many elements but still countable, just like the positive integer set. Countability is defined as if we can put a one-to-one correspondence with that set and the positive integers, then we say that that set is countable. Now, let's just give examples to uncountable sets so we can understand better. The water in a dam is a set with uncountable number of elements. So imagine a dam, and behind that dam, a huge amount of water is collected. That water creates a set. However, you cannot count the number of elements in that set. So that water is only measurable. We can talk about how many tons of water we have behind the dam. We can measure the water there. However, we cannot count that water. So this set is an uncountable set. Or the flour used in a loaf of bread is a set with uncountable number of elements again. So if you are going to bake a loaf of bread, you are going to use some flour for that. But that flour is an amount which is only measurable. It is not countable. You cannot count the flour. You cannot say how many flours we are using to bake a bread. You can only ask how much flour you are using. Now, the set of real numbers itself is also uncountable. Now, the positive integers itself is countable. Now, not just positive integers, we can say that all integers are countable as well. In fact, the set of rational numbers is also countable. However, the set of real numbers is uncountable. In fact, any interval subset, such as these unit intervals of the real numbers, is uncountable. Now, I cannot ask this question, how many real numbers do we have between 0 and 1? Now, we know that there are infinitely many numbers between 0 and 1, real numbers, and it is also uncountably many. So there are infinitely many and uncountably many elements we have between 0 and 1 as real numbers. So you see, sets are either finite or infinite. So they either have finite elements and infinite elements. Now, if a set has finite elements, then it is automatically countable. But if a set has infinitely many elements, then it may be countable or uncountable. Okay? Just like the integer set. Integers are infinitely many, however, they are countable. Now that we have understood the concept of countability, and this is a very important concept because it is going to help us to understand the distinction between the classes of random variables in chapter 4. So it is for your own good to understand the concept of countability. We are going to talk about experiments now. An experiment is a natural phenomenon whose occurrence can be observed, or a procedure that we can perform for examination purposes. Okay, for example, the weather conditions. The weather conditions are natural phenomena. So we do not have any control over the weather conditions, but we can observe the weather conditions. If it is going to rain or if it is going to be sunny, we can observe these natural phenomena. Or it can be a procedure that we can perform. Let's imagine this situation. We are solving a test which consists of 20 questions. Okay, so this is an experiment. We are trying to solve these 20 questions. This is an experiment, and our purpose can be to learn how many questions that we are going to be able to solve correctly. So out of 20 questions, how many we can solve. So this is an experiment that we have a control over it, but we do not have a full control over it. I mean, in the end, how many questions we are going to solve out of 20 questions is going to be random. Now, let's talk about the outcome. Outcome is the consequence of an experiment. For example, if you observe the weather condition tomorrow, if it rains, then the raining event is going to be the outcome. Or if it is going to be sunny, we will say that the outcome is a sunny weather. Or if you take a test which consists of 20 questions, and if you solve 17 of them, then you will say that my outcome is 17. So outcome is the consequence of an experiment. Now, there are different types of experiments, and we are going to be mostly interested in random experiments. A random experiment is an experiment that exhibits an inherent variation in outcomes. Or in other words, the outcome of which is not predictable in advance. Perform this experiment, this experiment may end up with different types of outcomes, but only one of them, okay? So we know the list of possible outcomes of this experiment, but the experiment is going to end up with only one of them. However, it is impossible for us to predict the outcome before performing the experiment. So let's try to understand this. If you take a test that consists of 20 questions, you may either solve none of the questions correctly, you can solve only one question correctly, two questions correctly, three questions correctly, so on and so forth. Maybe you will have the chance of solving all of them correctly, okay? So you see the outcome of this experiment, which is the number of questions that you will be able to solve correctly, can change between 0 and 20 in integers. But it is impossible for you to predict that outcome in advance. Therefore, this experiment is a random experiment because you do not know the questions before seeing them. So how many will you be able to solve correctly? It is also a random value. Now, let's focus on this experiment in this item. Throwing an egg from a building is an experiment. So let's just say you are throwing an egg from the 10th floor of a building, and what would be the outcome? Of course, the outcome is simple. The egg is going to break. So this experiment is not a random experiment. This experiment is just an experiment. In fact, we call such experiments deterministic experiments because the outcome of this experiment is predictable in advance. However, if your experiment is to draw 2 cards from a 52 deck, and that experiment is going to be a random experiment because if you draw 2 cards randomly from a 52 deck, you may have many possible outcomes. So you can, for example, draw a ace of spades and queen of hearts, or you may draw a 7 of clubs and 6 of diamonds. Okay, so there are many possible outcomes that you may observe if you perform this experiment, and it is impossible for you to predict the outcome, predict the cards that you are going to draw in this experiment. Therefore, we call this experiment a random experiment. Now, how many different possible outcomes do we have in this experiment? This is the question which is dealt by combinatorial analysis, the mathematical discipline of counting. So many problems in probability theory can be solved simply by counting the number of different ways that a certain experiment can result. So many probability questions are usually defined over random experiments. And in these random experiments, first we need to define the set of possible outcomes, and we need to be able to count the number of possible outcomes in these sets. Now, we are going to solve this question to understand the situation better. And this is going to be our first probability question, but it is just going to be a simple one, okay, just for us to understand how combinatorial analysis is related with probability questions. So in this question, we have a communication system, and it is going to consist of 4 seemingly identical antennas that are to be lined up in a linear order. So we are just going to put 4 antennas next to each other, but these antennas are very identical to each other in appearance. Now, the resulting system will then be able to receive all incoming signals and will be called functional as long as no 2 consecutive antennas are defective. So when you put these 4 antennas next to each other in a line, if 2 neighboring antennas are defective, then the system will not work. However, even if we have defective antennas in this linear order, but which are not next to each other, then the system will be functional. So if we want to have a functional system, 2 consecutive antennas should be defective. Now, let's just say you have 4 antennas and you know exactly 2 of them are defective, but you do not know which of them are defective. Because the antennas look like each other, you cannot distinguish which antennas are defective and which antennas are functional. You only know 2 out of 4 antennas that you have are defective. Now, with respect to operating status of the antennas, how many different orderings are possible? The question asks. So I have 2 defective and 2 working antennas, and I am going to put these 4 antennas in a linear order next to each other. So with respect to their working or defectiveness status, how many different orderings I can create? I'm just going to use these 2 letters, W and D, to represent a working antenna and a defective antenna. And I have 2 working and 2 defective antennas. Now, if I randomly put these antennas in a linear order, in a situation I might have first 2 antennas working like this and the third and the fourth antennas to be defective. So this is one of the possible orderings I may have with respect to working and defectiveness status. And this is the second example of a possible ordering. So I may have my first antenna working, second antenna to be defective, the third antenna to be working, and the fourth antenna to be defective. Another possible ordering that I may end up with is the first and the fourth to be working, and the second and the third antennas to be defective. Another possible ordering that I may end up with is the opposite of the third one, basically. The first and the fourth antennas can be defective, and the second and the third antennas can be working. And another possible ordering that I may end up with is the first and the third antennas to be defective, and the second and the fourth antennas to be working. And another one is the complete opposite of the first one. The first 2 antennas can be defective, and the third and the fourth antennas can be working. Now, even if you try to find another possible ordering, you will not be able to, because these 6 possible orderings are basically all possible outcomes of this random experiment. Okay, so we have basically created a list of possible outcomes of this random experiment with respect to working or defectiveness status. We have 6 possible orderings that we can create with respect to defectiveness status of the antennas. Now, let's skip to the second part of this question. How many of the above orderings will yield a functional system, it asks. Here in the first, in the third, and also in the 6th ordering, you see that the system will not be functional. Why? Because we have 2 consecutive defective antennas in these systems. However, in the 2nd, 4th, and the 5th systems, we have defective antennas separated out with at least 1 working antenna in between. So first, third, and the 6th systems will not be functional. They are going to be non-functional. And 2nd, 4th, and the 5th systems are going to be functional. Finally, the last part of this question asks us the probability that the resulting system will be functional. So with what probability? What is the probability of the resulting system will be functional, it asks. Now, in order to answer this question, we can just build a simple logic. We know that there are 6 possible orderings that we can create, but in only 3 of them, the system is going to be functional. Therefore, we can say that out of 6 possible orderings, 3 of them is going to be functional. So we can say 3 out of 6, or as a ratio, 3/6 as the probability of having a functional system, which is going to be 0.5. So you see, in order to answer this question, what we have done is basically we have counted the number of possible outcomes with respect to defectiveness status of the antennas. And then we have counted the number of possible functional systems. And the number of possible functional systems is divided by the number of possible orderings, and that has given us the probability of having a functional system. So this is how we have calculated probability. Therefore, in real life, some probability questions can easily be answered by just counting the number of outcomes in a random experiment.